In physics problems, we often encounter astonishing massless strings, which of course don't exist. Nevertheless, the massless string approximation is often very useful to us, and we should try to understand it. So I'm going to organize this discussion around 4 questions. Question 1, what is tension? If we consider a string to be a system, then tension could mean that external contact force that this hand is exerting on this end of the string, pulling it to the left. If the hand is pulling on the string, then of course we know the string is also pulling right on the hand, and that Newton's third law contact force pair, that could be considered tension. So we have a tension at either end of the string due to these interactions with external objects. But tension could also refer to what's going on inside the string, holding the string itself together. If we take any section of the string, a little segment like this orange one right here, and that little segment is being pulled to the left by this segment, it's being pulled to the right by this segment, and if that segment is being pulled upon, then it's also doing some pulling, so it's pulling on this segment and pulling on that one. So what we've got here are internal force pairs, Newton's third law internal force pairs, that are also referred to as tensions. So in this way, we can define the tension at any point inside the string as the contact force holding the 2 neighboring sections of string together. That's tension as well. Now, when tension is high, we say that the string is taut, and when tension is low or 0, we say that the string is slack. Okay, question 2. When can a string be treated as massless? There are 2 conditions. If we meet either one, we can use this massless string approximation. Condition 1, when the weight of the string is small compared to the tension on or in the string. So this string is under low tension here, the way it's hanging. If we do a free body diagram for this little segment here at the bottom, here's its weight. If we know that this segment has mass, so it has a weight, a force of gravity on it. And if that weight is not small compared to the tensions pulling on either end of it, those internal tensions there, then this string cannot be treated using the massless string approximation. Here its weight is important. But if we take that same string and pull it taut, so it's under high tension here, then on the free body diagram for this little segment in the middle, its weight is very small compared to these huge tension forces pulling on either side. So the force of gravity being negligibly small compared to the tension allows us to treat this string under these conditions using the massless string approximation. The second condition under which we can treat a string as massless is if the string is pulling on something that is much more massive than the string itself. So if the mass of the string is much less than the mass of what it's pulling, then we're also justified in using the massless string approximation here. So, question 3 then, what's useful about this so-called massless string approximation? Let's look at that anvil being pulled by our string here, and suppose they're moving along a frictionless surface being pulled with a constant acceleration to the right. Let's look at our string, and there's a tension on the right from the hand and a tension on the left from the anvil. Or we could look at a segment of the string and the tension on the right from this segment and the tension on the left from that segment. So if we're either looking at the whole string or the segment, we'll say it has mass m. Now let's do Newton's second law for either that whole string or just the segment. That looks like this. The acceleration of the string is due to the tension on the right minus the tension on the left. And we can rearrange this to multiply both sides by the mass to get this expression. And now, here's the argument. If the mass is negligibly small, if the mass of the whole string or of the segment is tiny, if we can set it to 0, then that's implying that the difference between the 2 tensions is 0. That's implying that tension 1 equals tension 2. And that's the most important conclusion from this video. The tension is constant throughout a massless string. Tension will be the same at every single point inside the string if we're using this massless approximation. And when you're reading through a scenario, a good clue to you that you can use the massless string approximation is if the string is described as light. A light string, that's suggesting that its mass is negligible, and the tension will be constant throughout it. Here's another way to show this, another argument to reach this conclusion here. Again, the anvil and the string. Let's look at the free body diagrams for each one. Just in the x direction, though, we'll ignore any vertical forces. So here's the anvil being pulled by the string, and the string being pulled by the anvil. That's a Newton's third law of force pair, so those are equal in magnitude. And then here's the string being pulled by the hand on the right. N2L for the anvil. That force divided by the mass of the anvil, capital M, that's our big mass. And then here for the string, difference in the tensions divided by the small mass of the string. If the anvil and the string are moving together, if they're moving as one, then their accelerations must be equal. So we can set these two expressions equal to each other, as I've done right here. Now I'm going to rearrange this algebraically. So at this point, I recommend you pause the video and look through my lines of algebra here as I go step by step to rearrange this expression into this one, where now we're showing how the tension on the right of the string is related to the tension on the left of the string. Here's this proportionality constant, this combination of masses. Now, let's say that if the mass of our string is very small, much less than the mass of the anvil, like if, say, the mass of the anvil is 1 trillion, and the mass of the string is 1, then 1 trillion plus 1 is still about 1 trillion. So m plus m is still roughly just the mass of the anvil here, so we can replace that with just big M, which then cancels. This is 1. And we conclude that under those conditions, if the mass of the string is negligibly small, then the tension on the right end is equal to the tension on the left end. That is reinforcing this earlier conclusion that the tension is indeed constant throughout a massless string. All right, that's our main conclusion. Now just a couple of words about how to treat a string wrapped around a pulley. Because we'll often have a pair of objects connected by a string wrapped around a pulley, either like this or like that. So under these conditions, the two objects will each have their own velocities and accelerations. And we can note that if our string is inextensible, as in cannot be extended, if our string doesn't stretch, if it's not stretchy or elastic, if our string's length doesn't change, then that means the masses are going to move as one. These two masses will move together, and these two masses will move together in such a way that their speeds are equal and the magnitudes of their accelerations are equal. So even though the accelerations and speeds are changing direction because of the string wrapped around the pulley, if our string doesn't change length, if it's inextensible, we can state this. Okay, lastly, if the pulley itself can be treated as massless, and that we'll have to discuss another time. Here again, that term light, if the pulley is described as light, that's a clue to you that you can treat that pulley as massless. So if this wheel has a very low mass, if the wheel is light, then that implies that the tension is still constant throughout the string. If our string is massless and the pulley is massless, then the tension is the same all the way throughout the string, even though the string is wrapped around the pulley and changing direction. This picture kind of reinforces that. So here's our string wrapped around a pulley. Consider this section of string right here in orange, and it would be pulled by tension by the two neighboring sections of string, and also feel a contact force, a normal force from the pulley pushing on it that way. Here's that free body diagram for that orange segment of string. And we can see from the symmetry that this normal force would be at 45 degrees and have components that exactly cancel the two tensions here and here, and the components being equal, that suggests that these two tensions here are equal in magnitude. So once again, the tension is constant throughout a massless string, even if it's wrapped around a massless or light pulley.